Hello, everyone. Thank you so much all for being here. Today, we have a pleasure to have David Kipping as our speaker. He will talk about his work focused in searching for exomoon with Hubble Space Telescope and also James Webb. He received his PhD from the UCL in 2011. Then he moved in United States for doing 4 years of the postdoc in Harvard University. And finally, he joined to the Columbia University as an associate professor. Addition in his work, which is focused in searching for exomoons, he did also remarkable work in outreach work, as particularly with creating his YouTube channel with the name of Cool World Lab, where he shared his research with wider public. Thank you so much, David, for being here. The stage is yours.
Thank you very much. I'm going to talk about exomoons today. It's been, I think, 16 years since I was here. So when I was doing my PhD at UCL, I was collaborating with Jean-Philippe, who was a good collaborator of mine, and still we chat often about exoplanets. And the idea then was we were thinking a little bit about the combination of microlensing versus transits. And over the years, I've sort of gravitated, to use the pun, more and more towards the idea of using transits, which is what I'm going to tell you about today. In addition to this work in my team, we do all sorts of other stuff, especially to do with astrostatistics, looking for technosignatures, thinking about life in the universe more broadly, and really just how we can even turn that search into a scientific question. And a lot of that has born from this work. By looking for exomoons, which is a very high-risk thing to do, you have to not only be willing to take a bit of a gamble, but also think really hard about the statistics, especially when you do a first detection that requires a lot of deep thought about all the possible confounding factors. And I think that's definitely true for life as well. So today's talk, what we're going to do, we're going to break down some of the different methods that have been proposed to look for exomoons, a little 101 class. Then we're going to talk about some candidate signals that have been found by my team. And then I'll talk about some of the most recent work happening with, for example, with James Webb. Okay, so there is a lot of different methods that people have proposed to look for exomoons. It's a really confusing landscape, actually. If you're a grad student entering this world, this can be a lot. I mean, you look at all these different methods, and we've got things like right in the front, we've got a microlensing detection right in the center. I'm sorry, I don't have a laser pointer to guide the eye here, but right in the middle, you've got an example of a microlensing detection. On the bottom right, you've got one of the first methods ever proposed that was using pulsars. So obviously there's pulsar planets. You can actually also detect moons using pulsar timing. You need very, very, very precise timing to do this. I don't think anybody's actually ever tested this technique. I'd love to see somebody actually put upper limits on a pulsar moon. As far as I'm aware, no one's ever done that. But the theory exists for doing it. And the very sort of top left, you've got the Kenworthy Mammajack one over there. That was actually a real claim for possibly exomoons by looking at disk structure around a single transiting, probably a brown dwarf. There's a single transit of this object, and it has all these intricate dips and wiggles around that transit. And it has been suggested that those dips and wiggles are ring structures. This is like a 1 AU ring, just an enormous ring. But those rings could be carved out by moons. So lots and lots of different methods. I won't go through them all because we can talk. If you have interest in any one of them, you can let me know at the end. But I do think this, if you're a grad student entering the field, this can be a bit of a confusing landscape to know, like, where do I start? Which method should I be using to look for exomoons? And it wasn't that way when I started the field. There was only just one or two methods. So we're going to zoom right in on just what I think is, in my biased view, the best way to look for moons, and that's going to be transits. And there's three reasons why I would try to convince you of that. One is that it is hands down the most successful method, clearly, of looking for exoplanets. And it is sensitive to planets down to the size of the moon. So we don't really need like a jumping technology to get to moon-sized things. It's already sensitive to that kind of scale. Second, and really important, which a lot of the other methods don't have, is it produces a falsifiable hypothesis. It produces repeatable events which we can falsify. So let me give an example which I think doesn't quite satisfy that, and that's to look for infrared excess, spectral energy distributions. So you could look for a volcanic Io, by taking the spectral energy distribution of an exoplanet and seeing like an extra bump and saying, oh, that must be a moon. But it's very hard to distinguish whether that's really a moon or, say, a ring system or just some other accreting matter onto a young planetary system. Whereas with transits, when we model these, the moon is moving. So if we detect the moon on the right-hand side in one transit, the next time it should be shifted over to the left and keep moving around. So I can make a verifiable, falsifiable prediction about the location of the moon based on my model. And if I make an observation and it's not in the place I said it should be in, precisely the place it should be in, my theory is discounted. I think that's one of the great powers of using transits, that we can truly falsify these hypotheses, which is, of course, as Popper would say, the foundation of science. And then finally, we don't have to build any new telescopes to do this. We can piggyback on existing telescopes because, as we all know, transits are getting a lot of attention with missions like Hubble and Kepler and James Webb. So we can just use that existing structure. The Ariel mission coming up, for instance, would be another good opportunity. So how do we do this with transits? Talk about some of the principles. So at the simplest level, the first thing you might think of is just look for the dip of the moon itself. And a group in Hungary, Gila Szabo and Tilla Simon here, have been writing about that for before I got started in the field. And they just point out that if you just add two transits together, you should get the dip. If you have, unfortunately, three disks interact, it can get more complicated than that because you can get syzygies. So a syzygy is like a total solar eclipse, right, where all three disks line up. And then you have to worry about the area of common overlap between the three disks. But we can handle that. We could think about techniques to do this. And we should be optimistic because we've got planets like Kepler 37b here, which is a moon-sized planet. So Kepler can detect these. I mean, naively, you would think, therefore, it's possible to find these kind of dips in Kepler data. So the first idea actually proposed was not to look for transits, though. I think it actually have to give credit to this paper back by Sartorati and Schneider, who suggested, I think this was work done at the IAP, who suggested that TTVs would be the best way to do this. So yeah, TTVs was not, in 1999, no one was talking about TTVs. This was I think this might even be one of the very first instances of someone even using that phrase, transit timing variation. We now associate TTVs with planet hunting, but really a lot of its birth was with moon hunting. So if you just think about a simple system of a planet passing in front of the disk of its star, and here I'm going to take a snapshot where the center of mass between the moon and the planet is just at the ingress point, right? It's just starting to make its transit. Now, because the planet is slightly offset from that center of mass, you can see that it actually comes into transit a bit earlier than the center of mass does. And vice versa, I can imagine a second epoch. So it gets shifted over. And I can imagine a second epoch where it comes in a little bit late in this case because it's been shifted over to the left. And so these red and blue are actually the wrong way around on those two transits. But you get the idea. The transit will shift back and forth as a result of the reflex motion around the center of mass. This is a really beautiful calculation to do in an undergraduate class. I'm not going to go through it quickly here, but it is fun to... Undergrads can do this TTV derivation from scratch with just Kepler's laws. It's very nice and easy to do, just balancing pivots, essentially. The most important thing for us is that it scales. If you look at the proportionality, it scales with AS, which is the semi-major axis of the satellite. So the further away the moon is from the planet, the bigger the pivot. So therefore, you're going to get a larger signal. And the mass of the satellite itself. The bigger the mass of the satellite, the bigger the signal. So it is like astrometry. I'm sure we've got some astrometry interested people here. The astrometric method of detecting planets has the same proportionality. This is not astrometry. I don't know what you'd call it, maybe planetometry. We're like measuring the position changes of the planet in the conceptually the same way that astrometry does, but using the transits to ping that. So for the Earth-Moon system, it's about a 2.5 minute signal, this amplitude, which is eminently detectable. So of course, we don't just do one or the other, we do both. And so we have written codes like Luna, which I wrote many years ago during my PhD. This is just an example of some of the simulations from it. So this is 6 transits, and this has everything in it. And so we call this a photodynamical simulation, because at every single time step, we really evolve the planetary system and calculate where the disks are and calculate the area of overlap and the limb darkening, et cetera, et cetera. So this is still essentially the state of the art. There's lots of, you can do this for planets. You can do this in the TRAPPIST-1 system, for instance. You might do something like a photodynamical algorithm. But for moons, it is essential to capture all of the minute signals, compound them together to maximize your chance. You'll notice some interesting stuff here. Like if you look at the penultimate transit, not the last one, but the one before, you'll see the moon, I wish I had a pointer, the moon comes over. I don't see a stick. Is there a stick somewhere hidden? I don't think I could reach, even if I had a stick, I wouldn't be able to reach up there anyway, to be honest. So anyway, that penultimate transit, you can see the moon happens on this side, right? It comes in early. The moon comes in early. And if you look at the planet comes in late. So you always get that antiphase behavior. If the moon comes in early, the planet comes in late, and vice versa, because of course they're going around the center of mass. So just keep that in mind for a little bit later on. Okay, so one of the observational consequences then of moons would be transit timing variations, TTVs. And guess what? There are a lot of TTVs in the Kepler data. So amongst a sample of 2,600 Kepler planets, over 2,400 of them, almost all of them, have TTVs at some level or another. TTVs are everywhere. They're very, very common. I don't think it's widely appreciated just how abundant TTVs are. Planets almost never follow strict Keplerian orbits. They're pretty much always in multi-planet systems of some kind or another, and they're always being perturbed and showing these little deviations. So this is just showing you kind of a log-log plot where you've got the period of the planet on the x-axis, so in log base 10. So 1 is 10 days, 2 is 100 days, for instance. And you can see that TTVs of order of a minute to sometimes hundreds of minutes are present all over the Kepler data. What I'm showing you with the color scaling is if we assumed all of those TTVs were due to an exomoon, how far out would the exomoon have to be? Because obviously, the bigger the TTV signal, the further away I have to put the moon in order to explain it. And you can see here that actually the vast majority of these are consistent with basically being within the Hill sphere. So there's no reason why almost all of these couldn't be exomoons in principle, although I certainly doubt that's the case. But there is a huge gold mine of untapped data. And for the vast majority of these TTVs, there is no solution. There's no published solution for 90% of these things. So that's important. So let's talk about what has been found, what the current state of the art is with existing surveys. I'm going to move on to my candidate section here. So I've been searching for moons for a long time. I can't possibly summarize all the work I've done, all the different papers we've published looking for exomoons. So I'm just going to focus on a couple of particularly interesting ones. One idea we had a few years back, and a few people had this idea, was that you could stack hundreds of transits together, and if a population of planets had a population of moons, you might be able to see like a global dip, some kind of average dip in all of the signals. So we tried that. And so we actually stacked about 300 planets together, and we couldn't see anything, unfortunately. But amongst that 300, we did see something interesting. That was this one object, Kepler 1625b, and this is sort of the significance histogram of all of our objects. And this one object stuck out there at +4 sigma. So that seemed interesting. There was some kind of dip. This is not using TTVs. This is just using dips in starlight. There is some kind of dip associated with that planet that isn't bang on where the transit of the planet happens. So we got interested in this object. However, we were suspicious because the dip would be huge. It would correspond to a Neptune-sized moon, which, I mean, who ordered that? There's no prediction in anyone's theories of Neptune-sized moons forming. So that would be a hard pill to swallow. However, when you look at the properties of this planet, if I sort of ping where it is, it lives right up here. So in terms of period radius of all the planets we know about, all the colored dots, these are all Kepler planets. And the colored circles are planets which could dynamically hold onto a moon for at least 4.5 billion years, I think we assumed here. So they could dynamically, through tidal migration, hold onto moons for a long time. And those moons would be detectable given Kepler data. And amongst all of those, Kepler 1625 is the most Jupiter-like planet in that entire sample. So a priori, it seemed really tempting that this could be a great exomoon target. It's a 1 year period almost, 287 days, and it's a Jupiter-sized planet. So that's kind of the exciting regime for having an exomoon. But of course, we didn't feel convinced by the Kepler data. That histogram's not enough. So we wanted to get some Hubble time. And so let me show you that. So we got Hubble time. This was 2018. I think we got this data. And the first thing we notice is that if you take the 3 Kepler transits shown on the left-hand side and you try to draw a strict linear ephemeris through them. So this is the timing of when those first 3 transits happened. So this is TTVs. We're looking for the TTVs of these planets. If you just draw a strict straight line through those first 3, which is what that line is, it beautifully matches a linear ephemeris. There's no evidence for TTVs. But when you add on this new Hubble transit right over on Epoch 7, it comes in way too early, 78 minutes earlier than it should do. And so we have strong evidence just from that one transit that there is definitely a TTV in this system. Obviously, you can sort of redraw the ephemeris and get a better TTV out, but there is certainly a TTV there. Now, remember, if the planet comes in early, which it does here, we would expect the moon to come in late because they always have this reciprocal relationship with respect to the center of mass. And that's what we see. So you look at the transit and you see, shown in the top right there, this dip that occurs towards the end of our observations. Now, unfortunately, the observations don't continue. Obviously, it'd be great if we had, a flat, it would come back up and it would flatten out for a while and we'd have a bit more data. But we only had 26 orbits, which is still a lot, 26 orbits of Hubble, 40 hours of continuous observations with the Hubble spacecraft. And so you see this second dip occur about 3.5 hours after the transit. And the size of that dip is about a Neptune radius, which is what we'd seen before already in the Kepler data. And the TTV mass that you get from that is also about a Neptune mass. So despite our skepticism that such a thing is possible, everything in this data keeps pointing at the same type of moon. And this is formally very significant. So we don't need to worry too much about significances here. So there's a lot of positives here. I mean, some of the things are that the centroids are extremely stable during the moon dip, for instance. There's no South Atlantic anomaly that occurs during that moment in time. The moon-like dip occurs in both the blue band and the red band. This is the power of having a spectrograph, of course. You can actually check whether signals in all your different colors. And we know this is not another planet. So you might say maybe another planet has photobombed your observations. This is just another Neptune that just happens to pass in front of your star at the same time. We can also rule that out based off the previous Kepler data. So this is pretty interesting. The TTV was also independently recovered by 2 of the teams. But of course, there's a lot of controversy, as anyone who's followed this story might know. And so there's been multiple papers which have chased this back and forth. So there's, first off, there was a paper by Laura Kryberg and her team who did their own analysis, and they were not able to see, well, they still saw the moon dip, but it wasn't as big. They got a smaller moon dip, and so they were skeptical about that. The René Heller paper showed here actually gets almost the exact same dip that we do and the same TTV we do, but they just think it's a hot Jupiter. I don't really understand why they think it's a hot Jupiter, but they seem to think it's a hot Jupiter. We actually have RVs we haven't published yet that completely exclude that it's a hot Jupiter, so I'm 100% sure that's not the right answer. And so we've responded to some of these papers, and we can get into that in the end if you're really interested, but I could spend like literally 2 hours talking about the back and forth. It's not really interesting. I think the main reason I'm personally skeptical is that we only have a single transit, really. The Kepler data is just pretty noisy. It's not really convincing. This is the only clean dip that we have that you can look at. And one transit is just not enough. And no one's going to be convinced with one transit because there's always possibility the telescope does something weird in one transit. So we actually asked Hubble after we got this, look, this is a clearly predictable model. If this moon is real, the next time we observe it, it will be over on this side of the screen instead. It will shift over. I can tell you exactly where it should be. And if it's not there, we can all move on with our lives and forget about this thing as being a real exomoon. And they did not give us the time. So we were like, okay, how are we supposed to disprove our own hypothesis? And then we tried again. We got rejected a third time. And so now it is so far in the future since this observation that we have no idea where this moon would be anymore, because of course the uncertainty grows over time. So we can't even falsify this anymore unless we just went back to scratch and got 2 new transits all over again. So it's a very frustrating situation to be in. And I think it goes to show you how difficult it is, honestly, just politically to do this kind of work, because if you're not doing atmosphere work with these big telescopes, looking for moons is just considered super high risk and not particularly interesting. So I've been struggling against that for a while. It's been a frustration. But there was a lesson from this, and that was that this planet, the one planet that gave us any hint of an exomoon, happened to be the most Jupiter-like planet we'd ever seen. And so based off that, we decided, let's just focus on the Jupiter-like planets, because that seems at least, obviously that's the best hunting ground. So we did another survey, and after years of searching, I can tell you that probably things inner to 0.1 AU, hot Jupiters, I've not surveyed for moons there. I don't know too many people who have, and I think it could be worth doing, but I don't know whether there's moons there or not. But between 0.1 and 1 AU, we have hit that region pretty hard, and moons are not common there, down to Earth mass, certainly. There are just not a lot of moons in that region, otherwise we would have found them by now. Beyond an AU, we only really have that one example of a planet that we've looked at, and that's barely an AU, even in that case. So we decided to make a new sample, go through Kepler, get all the planets which are basically beyond a year, beyond an AU, and are greater than half a Jupiter radius. And so there's actually 70 in the Kepler sample. Out of the 5,000 that it found, there's about 70 which satisfy that criteria that have 2 transits. I need 2, otherwise I don't know the period, of course. So looking at those, we did our photodynamical fits and we looked for moons. And this is the best object we found. So this object, there's only 2 transits, and I'm showing you the same 2 transits 8 times on each side of the screen. And I'm detrending the Kepler data in 8 different methods. Because sometimes you might wonder, well, maybe if you detrend it a different way, you get a different result, like maybe that influences the assuredness. So no matter how we detrend this signal, if you look at the chi-squareds, that's the chi-squared evidence in favor of an exomoon. And roughly if you square root that number, that's your sigma significance, right? So you're looking at something around about sort of 3 to 5 sigma significant in this signal. And that's the best we could do. No, because the moon doesn't have to transit every time. Yeah, the moon doesn't. I mean, actually, the moon is slightly in here. I can't really see my cursor, but if you look, there is a slight bump. If you look at the very bottom left corner there is a tiny bump, and it comes in on the shoulder on the egress. You can see that tiny bump. Yeah, so that's not a particularly. The second transit isn't particularly convincing. Most of the signal is driven by that first event, which is that step function and the pre-transit shoulder. So you're right to be skeptical, but this is the best object that we have, and it's of order of 3 to 5 sigma. So obviously, there's lots of 3 to 5 sigma signals in history which have disappeared. So we should definitely be cautious about that as well. Oh, I don't know. I'd guess around of order of the scatter, I would assume, but yeah, I'd have to pull that up to show you. So one of the reasons I was skeptical about this being a real moon is because we'd actually killed another exomoon in the past using the following centroid test. So on the left-hand side, when I'm showing, on the right-hand side, sorry, I'm showing you the flux image that Kepler caught. That's the actual image that Kepler took of that star. And the black box is the aperture that it used to derive the photometry. Now, as you expect, most of the light occurs inside the box, right? Because that's where the star lives. What we can actually do is for every single one of those pixels, there's only, how many pixels? Like 20 pixels there. For every one of those pixels, we can make a light curve, and we can measure a transit in every one of those light curves. And we can ask, what is the signal to noise of the planetary transit in every one of those light curves? And that's what that middle panel is. So as you'd expect, most of the planetary transit lives where the star lives, which is good. I mean, obviously that should happen for a real planetary transit. On the right-hand side, we did the same thing for the moon. And for the previous object we'd killed, Kepler 90G, this thing lit up like a Christmas tree. Like every pixel was just on fire. So basically, that doesn't make any sense. Like there's no reason why pixels way outside the aperture should be contributing towards the exomoon signal. But here it really does look like this signal lives in the same location as the star. The other thing we tried was a false positive test. We'd never done this before because usually it's actually really difficult for various reasons. But because we have 4 years of continuous photometry of this star that has all of the real stellar variability baked into that 4 years of data, we could take our planetary transit and we can inject it at different random times, just a planetary signal, no moon, and we can run all of our models through it and ask how often do we screw up? How often do I erroneously claim an exomoon when there is nothing there, which is the false positive rate? So when we do that, we find from 200 injections, 2 recoveries. So a 1% false positive rate. And this is an extremely frustrating number. I kind of wish it was just either like 10%, in which case we could just be like, okay, this is probably not real. Or if it was like 0.1%, in which case it'd be really interesting. But to be 1% is like right at that threshold. I mean, this is actually the same false positive rate that Kepler used for validating planets. If this was a planet, this would be called a validated exoplanet by Kepler standards. I mean, this is the first thing of its type, so I would definitely not be confident calling this a real exomoon based off this, but it's right on that hairy edge. So the best way to describe it is what I've written on the top corner there. I can find personally no way to prove this is not real. That doesn't mean it is real, but I can't find a way to kill it. We've tried everything we can think of to try and kill it, and we can't find any obvious red flags. That still does not mean that this is a confirmed exomoon. We obviously need more data, more observations to confirm it, but it remains a candidate which is very robust. So these are the properties of it. It's about a 2-year period, a Jupiter-sized planet with a sub-Neptune-sized moon. So again, a very large moon. I will say, by the way, some people get annoyed about these large moons, and I think you're right to be concerned about the reality of making such a large moon. But by historical context, hot Jupiters were also not many people's cup of tea when they were first announced. A lot of people had deep reservations about the reality of having a Jupiter-sized planet parked that close to a star. And in hindsight, it's not surprising that hot Jupiters dominated early detections, even though they're very rare. Less than 1% of stars have hot Jupiters. But they dominated early detections because they're so damn loud. They have massive signal to noises. So it shouldn't be that surprising that the first exomoons, if these are real, would be not typical of normal moons. They would be unusually freakishly big and large because, of course, they're going to be the easiest ones to find. So let's move on and talk about what's been happening more recently with new searches. So I want to talk a little bit more about TTVs and then James Webb. So I think it is tempting to look at everything I've told you so far and think, well, there's just not many moons out there, right? Because, or not very big moons out there, at least. But remember, as I said, like one of the observable consequences of moons, a moon population, would be a TTV population. And we definitely do have a TTV population. However, the big problem is ambiguity. And so this wasn't really recognized at the time when Jean Schneider was talking about TTVs, but we now recognize TTVs as a hallmark of multi-planet systems. Resonance systems especially have these TTVs all over the place. And so the real problem is ambiguity. If you have a TTV, is it a planet plus a moon, or is it a planet plus a planet? Like, how do you tell the difference? And that should sound familiar to anyone who studies planets, because we have the exact same problem with transits. If I show you a planetary transit or a planetary-like transit, it could be a star and a star that are causing that and not a star and a planet. It could be a confounding factor. It could be false positive, eclipsing binaries, hierarchical triples. There's all sorts of ways which stellar physics can mimic the type of signals that planets have. And this is a solved problem. So if Kepler figured out how to solve that, they they created these simulations where they would just create every possible, eclipsing binary you can imagine in the computer, every possible hierarchical triple you can imagine, and they'd count up what fraction of those simulations matched the observations versus a planet-planet model. And this kind of gave birth to what we now recognize as the planet validation paradigm that we've been in since basically 2011, 2012. And so you see these two huge spikes that occurred in Kepler's detections. In 2014, 1,000 planets were validated in 1 year. And that's when this blender software, it was called, was developed, that was able to rapidly validate thousands of things all at once. And then again, Tim Morton did a second paper in 2016, where again, he bumped it up massively. So this changes a little bit the paradigm because these aren't confirmed planets, these are only statistically validated planets, but maybe that might give us some hope that we could do something similar with TTVs, that we could compare different models and ask statistically how likely is it that each of these TTV signals is caused by a planet plus a moon versus planet plus a planet. So we've been thinking really hard about that, and it's a really interesting question. So Daniel Yahalomi, he's just graduated with me as a PhD student. He's now a postdoc, moving on in his career, but continuing this project. And there's a couple of reasons why we have some hope here. One is a technique which I call the exomoon corridor. And this exploits a sampling effect. So whenever you see a transit, that's your opportunity to measure a TTV. You can't measure TTVs the rest of the time. When it's over here, when it's behind the star, I mean, you get a secondary eclipse then, but it's very noisy. The only time really you have to measure a transit timing variation is when it transits. And so the frequency of your sampling is limited by P subscript P, where that's the planet, the period of the planet. Now the moon will always have a period much shorter than that of the planet. Right, think about the Earth-Moon system. It goes around once a month, but the Earth goes around the Sun once a year. And that's generally true for any stable moon system. It has to be in a much shorter period. And so therefore, it turns out it will always be a faster rate than the Nyquist sampling rate. So you're always going to have an undersampled signal. So what happens when you have undersampling to the signal? Anyone know? It's a bit louder? Anyone? I hope people don't like being put on the spot, sorry. You get aliasing. You get aliasing of the signal. So the signal will be aliased. So here's an example. On the top, I'm showing you an example of a TTV caused by an exomoon, and the gray line is the true TTV that the moon is generating. So it's a very rapid signal, but you only get to sample it at those integer points where I've put a black circle. That's the only points where you get to make a sample. And so as a result of that, it becomes undersampled, and so the best fitting line through it, the red line, is not equal to the true frequency. And so if you do a Lomskargel periodogram, which I'm showing the bottom of that data, that's exactly what you'll get. You'll get a spike at around 4 cycles, but the true period is less than 1 cycle. But a periodogram is normally run from the Nyquist frequency, which is 2 cycles and out. So you just can't see this as a real signal. So this is interesting. Exomoons are always undersampled, but you can actually predict exactly what the TTV would be. This is the effect of aliasing on your signal. This is actually well known. I got this from radio velocity. In radio velocity, they often have a similar problem. If you take a sample once per day, which people often do, you only go to your spectrograph once per night. You measure your star once per night, but there's an ultra short period planet there that's on a 0.7 day period, let's say. It's going to get undersampled in your RVs by the same effect. So this is actually where I kind of stole this idea from. So the same thing is going to happen here. And it turns out, and this is remarkable, this is maybe useful for RV people as well with this sampling problem, any aliased signal, irrespective of the intrinsic distribution, will follow this probability distribution for the aliased signal. So the aliased signals will pile up towards the Nyquist rate, if you look at that. So the Nyquist rate is 2. And most of the signals that you recover will be there. And it turns out this is true no matter what the probability distribution of the satellite periods are and the planet periods are. So you could assume that moons tend to live really close to the planets with an exponential distribution. Or you could assume they follow a uniform distribution across the Hill sphere. Or you could assume a log uniform distribution. It doesn't matter. Whatever continuous distribution you use, it will always produce the identical histogram here, which is like a remarkable feature of statistics. This happens. So this has some interesting consequences. It means that 50% of the signals will be between 2 and 4 cycles. So therefore, even though we don't know what the distribution of exomoons in the universe is, we know with certainty that 50% of them will generate a TTV that lives in that range, as manifesting in our data, because of this aliasing effect. And what's interesting about that is that is not a normal range for a TTV. So this is the histogram of all of the Kepler TTVs that have been confirmed. It's on a log scale, and that empty black histogram shows the aliased exomoons that I just showed you, and you can see they're very different distributions. And this should also not completely surprise us, because if you think about how most of those planet-planet TTVs are generated, it comes from near-mean motion resonances and libration effects that happen as you get close to resonance. So what happens is, if you're actually bang on a resonance, you're like an exact 2-to-1 resonance, the TTV frequency is infinity, and the TTV amplitude becomes enormous. This is why we can never detect exact resonant exoplanets using TTVs. Because if the period is infinity, it just looks like a straight line, right? There is no TTV. The further away you walk from a 2-to-1 resonance, you go to 2.01, 2.02, 2.03, the period squeezes down, it shortens. The amplitude drops a little bit, but most critically, the period has now become observable because it's less than infinity. So if you wanted to go all the way to the shortest possible period, you would have to live in the valley between 2 resonances. So you'd have to go like in between the 2-to-1 and the 3-to-2, like in this kind of like almost anti-resonance position. That would be the only way that you could possibly generate a very short TTV, and that's that purple region shown at the bottom. So this is just an inherently very dynamically unlikely place. Like planets should not be trapped in anti-resonance. They tend to prefer to get trapped close to resonance. There's no reason why they'd be shepherded into anti-resonance positions. And indeed, we see that manifest in the demographics. So this gives us some hope that we could potentially distinguish them. And so we actually found an object which lives in this exomoon corridor, and it seemed perfect for this, for maybe testing out this idea. So this object was called, Kepler 1513? I think, well, it was 3678 was the KY number, but now it's Kepler 1513. And so we've only got a handful of transits here. I think there's 7 or 8 points. But when you take a periodogram of that, shown at the bottom, you can see it's, and this is just 2 different reductions of the data. It's definitely a short period TTV to explain that from the Kepler data. So right in the exomoon corridor, just what we'd expect. And also look at the TTV amplitude. It's just a few minutes. A few minutes is really like the nice sweet spot for exomoons, where they're not so big they become suspicious. Planet-planet interactions often produce hours, even day-long TTVs. But a few minutes is exactly what a moon should be doing, something nice and small. Very high. Look at the significance. It's like square root 500, gigantic significance of a TTV here. So we got excited and we went to TESS to look for more transits, and we went to the ground and got more transits. And the story fell apart in our hands when we did that, as it so often does in exomoon hunting. So many cases of things disappearing. So it turns out that the signal we saw, that apparent short period signal, is merely the beating frequency of 2 frequencies operating together. So obviously, if you have 2 frequencies mix, you'll have an envelope and you'll have a beating. And what we saw was the beating. And there was, on top of that, there was an envelope frequency that we just couldn't see because its period was so long, it was decades, the period of that beating, of that envelope frequency, that you just can't see it in a 4-year baseline of Kepler data. It was only once you go to TESS and to the ground that you can see that second frequency. And that second frequency is the larger frequency in terms of amplitude. And that completely changes the solution. So it ends up being that it's now basically impossible for a moon to explain this. The moon model is the blue line. And you can see the blue line just cannot explain that penultimate point there. There's no way for the moon model to explain that. But if you do an n-body planet-planet solution, it can now explain that beautifully because of this effect. So very frustrating, but an interesting lesson that sometimes we are constrained by the finite baseline of observations when we're doing this work. So you can see something that looks like a high frequency signal, but it's actually not. It's just because of your baseline is too short. But one really cool product of Daniel's work on this was that not only did we talk about this exomoon corridor, we also discovered what we call the exoplanet edge. So it turns out when you do these millions and millions of n-body simulations, you never get TTVs below that line. So we call this the exoplanet edge. So it's impossible for a two-planet system to ever produce a TTV here. So I'll give you an example. This point right here, that's a real planet. Should be impossible. If you have a perturbing planet that is 25 times the orbital period of the inner planet, it should be impossible for that planet to generate a TTV of 6 times the inner planet's period. That's just not allowed. There's no possible configuration that would ever produce a TTV like that. And that's true of all of those points below that line. So this is a forbidden landscape if you only have 2 planets. And so all of those red points are almost certainly being perturbed by additional mass in the system to cause that. So in other words, any point that lies below here must either be a 3-planet system or potentially a moon, especially the ones that live right in that corridor, the exomoon corridor. The very fast frequencies, remember, are pretty unlikely to be a planet-planet interaction because that's just not a particularly favored situation. So we think there is some hope. Hopefully I'm convincing there is some hope of thinking about the dynamics very deeply, that you might be able to statistically validate whether TTV signals are really moons or planets using these ideas. So finally, I'm going to talk about James Webb. And probably for me, the most interesting target there is still for looking for exomoons would be this planet right here, Kepler 167e. It is the most Jupiter-like transiting planet we know of, full stop. At least, and that's just something in the archive the last couple of days I've missed. This is a really outstanding planet. It's 1.01 Jupiter masses. Look at that abstract in the bottom line there. 1.01 Jupiter masses. Its radius is 0.91 Jupiter radii, and it lives beyond the snow line. It's on a 1,000 plus day period. It takes 3 years for this planet to transit its star. That's really, really long by Kepler standards, a 3-year period. And its star is a K-dwarf. So that means that the star is even cooler than the sun, and therefore, the habitable zone and the snow line all come inwards compared to the solar system. So this thing is way out beyond the snow line boundary. It's probably of order of about 130, 140 Kelvin. So a very cold Jupiter-like transiting planet. And there's not very many of those that we have access to. So, and it's also fairly bright. It's about 12th mag in Kepler. So we asked James Webb to look at this, and we only published this work a couple of weeks ago. And this was the observations we took. Now, you notice a few things. There's these detector resets that you can see, these little kinks in the data. So this was not something we really anticipated being such a big problem, but when we got the data, we saw how big this systematic was. Every 10 hours, the detector has to reset. We have 60 hours of data. So that means we've got 5 resets of the detector. And that's a digital effect. The detector just runs out of RAM and it has to reset at a certain point and flush everything out. Apparently this is totally fixable, and there's no reason why it has to be. They could actually observe much, much longer than they do. It's just like a safety precaution. So I think they're going to try and actually get rid of this effect going forward. But it was a real pain in the butt for us doing this analysis. And of course, during those detector reads, you also get this trend, which you can see. On top of that, of course, you've got this big, beautiful transit of 167e. I mean, look at that for a light curve, really high signal to noise. And then you've got an additional transit of C on the right-hand side as well. We anticipated that C would happen. And you can see the trends zoomed in on the bottom. So a lot going on here. The trends is where like the real meat and potatoes of this analysis comes in. Those trends, as anyone knows who's tried to detect something in a telescope before, trends, systematics are the bane of your existence. And that is absolutely true in this analysis. So we see these trends and we don't really know what the right model is. None of the ground-based testing suggests, oh, just use a quadratic line. It's all heuristics. People are just guessing. Nobody knows, and still they don't know. Typically, people use a linear line. That is by far the most common thing people do with these analyses. You can see clearly a linear line is not going to work for the, I mean, obviously it's got curvature. So we tried a quadratic trend, which is sometimes used. That's like considered the advanced thing to do a quadratic trend. But even a quadratic trend doesn't quite seem to capture all of the variations. So we tried a suite of different ideas. We tried an exponential model with an additional linear term. And that was kind of motivated by thinking about detector persistence effects that could be happening inside the detector. And then we also tried two kind of more agnostic models, Gaussian process models, a squared exponential, SE, and a Matern 3/2 kernel. And broadly, you can group those together. The quadratic and the exponential usually produce identical results, and the two GPs usually produce identical results, which is why I'm only showing you one here. So if you look at these four trends, we actually have six altogether, but these are the four that occur out of transit. You'll notice that I've got the chi-squareds for the moon model and the planet model in the corners there. You'll notice that the GP models always perform better than the other models. And that's not that surprising. GPs are inherently very flexible, so they tend to always perform a bit better when compared. But that is a persistent pattern that we see when we try to model these trends out. The other thing that we notice is that if we try 3 different reduction methods of reducing the data and 4 different trend models, in each case, we can measure a bunch of stuff. So that top number is the size of the moon that we measure. And I'm quoting these numbers relative to that of the planet. So it's the size of the moon divided by the size of the planet. So those top numbers are the size of the moon. And remember, in the top left, the planet is about 10 times that of the Earth. So if you just take 1 decimal place off those numbers, you've basically got the size of the moon in Earth radii. So for instance, that very bottom number, 0.179, you should read that as 1.8 Earth radii, essentially. That's a big moon in that case that it's putting into the system. And so all those green highlighted ones are, in principle, positive detections. And the numbers below are Bayes factors. So these are all positive detections, strongly detected signals. So 7 of the 12, across our grid of models, 7 of the 12 give us strong exomoon detection, which is intriguing. But what we notice is first off, that this JEDI reduction, exotic JEDI it's called, that seems to produce really big moons when you use the GP. Like those moons are way bigger than all the other moons by a long way, which is suspicious. And actually, when you look at what's going on, this is actually showing you the light curve with this correction added on. This is the custom reduction, where you can see on the top the trends, and then the panel below shows you what the moon's doing. So the moon dips in there on the ingress. But if you go to the kind of flick between these, this is the more trustworthy reduction, I would say, and this is the JEDI reduction. And look at what happens to the moon. It puts in this like gigantic upwards increase right in the middle of that trend. Do you see that? Right where the moon comes in, suddenly the trend like totally reverses. And it reverses in order to accommodate this giant moon. So this is very, very suspicious. This is obviously some weird interaction of the Gaussian process and the moon model, and this reduction being a little bit suspicious. So we started to think there's something wrong with this reduction for doing this. The other trick that we used is we can actually locate where that moon signal lives in a time space, in a chi-squared sense. So here are the 3 different reductions we tried. We tried our own custom algorithm, we tried ExoJEDI, and then we tried another code called Katadin. And you can actually see where does it put the moon signal. And the important thing to note about this is that the green one puts moons in places that the other models don't. Here and here, where those 2 arrows are, the JEDI model puts in moon signal that the other reductions do not agree on. So there's something this JEDI reduction is doing that the others are not doing. So we basically threw that out. We were like, there's something weird with this pipeline, let's not trust it. And then what's left over is this. You have, with the quadratic and exponential models, you have 3 out of 4 positive detections. And with the GP models, you have 0 out of 4 moon detections. And that's already suspicious. So just by changing the trend model from a strictly deterministic model, like a quadratic trend, to an agnostic probabilistic trend model, you kill the moons completely. So to me, that's enough. You know, any kind of drop of a hat that there's not a moon there, I'm walking away. It is interesting to see what's happening here a little bit more closely. When you look at these these four models, and I'm averaging them over the reductions, what you'll notice is that the only place where they all agree is the signal is right there. And those two vertical bands, that's the ingress and egress of the main transit. So that signal happens right in the middle of E's transit, right in the middle. And anyone who's looked at transits of variable stars will know that star spots are a big confounding factor for things like this. So a star spot will also cause a little upwards decrease just like that. So it looks very like a spot crossing. And not only that, the moon this corresponds to would have to be almost grazing the atmosphere of the planet. It has to be very, very close in to explain this. So we became pretty suspicious at this point. We looked at the Kepler data for the activity cycle, and there is no clear rotation signal in the Kepler data. But it is consistent with something up to a 1.3 Earth radius moon equivalent spot, basically, being produced in our data. And indeed, these signals are smaller than that. So it's totally consistent that the Kepler data could have spots in it that we just can't detect because Kepler's not sensitive enough, but would be enough in James Webb to produce this kind of false positive. So that's our takeaway, that this probably is not real at this point. But I think the big lesson, this is my final slide, is that one transit, as we've seen in both stories, with the previous exomoon candidate I told you about, and with this James Webb signal, one transit isn't enough. And yes, you might say, okay, you've got two Kepler transits, so you actually have three. The Kepler ones don't count, because the Kepler ones are so noisy compared to the James Webb ones that the James Webb one completely dominates your inference. So you may as well not even have those Kepler ones, to be honest. A single one is just not enough. A moon model is very flexible. It can put the moon in all sorts of ways. It can do all these syzygies. It can do all these kind of weird undulations. It's too flexible a model. If there's any slight deviation from white noise properties, it will capture that and it will say, bang, you've got an exomoon. That's a big problem. But it won't happen if you have multiple transits. With multiple transits, the moon has to be in specific locations each time and follow a strict Keplerian ephemeris. So we can break this degeneracy by having multiple transits. So I think we should go back in a couple of years, hopefully capture another transit of this thing. There's ways we can modify the instrument to get rid of those systematics a little bit. And of course, it'd even be nicer if we could do more than just one or two planets, because if you look at the story of exoplanets, we didn't just survey one or two stars and say that's enough to look for exoplanets. We surveyed dozens of stars, and it took probably hundreds of stars to be surveyed before we started finding lots of planets. And so by the same token, I know it's asking for a lot, but I'm sorry, Hubble and James Webb, you can't just look at one planet and hope to get a moon detection. We probably need to invest a bit more effort than just a one-off shot. So with that, I'll take questions. Thank you.
Thank you so much, David, for nice presentation. Any question?
Actually, it will be more a bit of a comment, and it's a comment addressed to the younger scientists in the room. Just would like to underline that when David decided to work on Exomoon, he decided by himself. It was not a suggestion from anybody. So this is a case where a PhD student decide to go off tracks and create something which is now where we are today. So congratulations for you too.
Thank you
for that. And it is also a nice message for the young scientist. Do you have more candidates actually beyond the one that you have seen that we could check that would be interesting to probe in the coming years?
Yeah, we do have other Jupiter-like transiting planets, not quite as good as 1670, not quite as Jupiter-like as 1670, but very close, that TESS has discovered. There's two cold Jupiters that TESS has found. And we have asked for telescope time to observe those as well in the last couple of cycles. It hasn't been successful either. It is very hard to get James Webb time at the best of times, and probably even harder when you're asking to do exomoon work. But I think there is hope, because I think the atmosphere people are getting increasingly interested in the composition of these cold Jupiters as well. And so there's a nice synergy there where both of us have the same interest in trying to move beyond the hot planets, the warm planets, and get to this regime where we can do some interesting dynamics, but also interesting chemistry.
Any other question?
Thank you for this wonderful presentation. I have a question. What is the possibility to observe from ground-based telescopes such features, and what minimum size you recommend for that?
Yeah, I mean, I think one of the best examples of that is this Kepler 1513 case. Let's see if I can get back to that. Yeah, I think this case is a really great example of the power of ground-based observers. Try and zoom in a bit. So this point and this point, one of these is uses tests. It's a fusion of tests plus a ground-based telescope, and this one is pure ground-based. And that is the data point which completely excludes the moon model. So I think what we really want to do is go after these large Jupiter-sized planets at long periods, so they very rarely transit, and try and catch an ingress or an egress from the ground, which is enough for us to get a reasonable TTV point. And that should be able to discriminate between these two competing hypotheses. So I think that's what I'd encourage those on the ground to try and capture. In terms of the actual specifications, we can talk about that a bit more after, but broadly in terms of target selection, long period planets, especially those that already have hints of TTVs, are really worthwhile pursuing from the ground.
Thanks for the nice talk. I'm going to ask the technical question because we spend all our time reducing viz data here at EIP. When you talk about different reductions, you don't mean the instrumental part, you mean the photometry, or what is it exactly? And it's kind of alarming that they all give different answers. So don't people know how to process the data yet? Sorry.
No, I think you're right. There is, the different reductions as well, just sort of show these three together. Here's like a hidden fact not many people realize. All of the reductions, all of them, are essentially the same reduction techniques. So they all use what's called the same stage 0 and stage 1 space telescope pipeline products. They all use exactly the same stage 0 and stage 1 products. And that dominates your result. The only algorithm which doesn't use those is this new one that we actually made, Katadin, which goes completely from the ground up in terms of building a whole new pipeline. That's the only real second example of a pipeline. But it is alarming, and it is true that we do not yet fully understand the systematics on board James Webb, and it's deeply upsetting to me. And I've been trying to tell my colleagues that we need to have workshops just about that topic. I'm not sure. I mean, there was calibration on the ground, but it's out of date. It's 4 years old, so. Hey. No, this is near spec. Near spec. Yeah. The anomalies? You mean in the middle of? Oh, the detector resets. I think so. Yeah, Miri has the same ones. Yeah, that's what I've heard. I've heard that in Miri it's been solved. In NearSpec, it has not been applied, but there's no reason why they couldn't do the same fix to NearSpec. That's what I've heard. Yeah, so I really hope that happens. To answer your first question about formation, yeah, I mean, theorists are very imaginative. So after we published our paper, even though there was no prediction of a Neptune-sized moon, multiple papers were able to explain possible ways of making such a large moon, as always happens with theorists. One is a very, very massive circumplanetary disk. If you make the disk massive enough, you can form arbitrarily large moons from it. A more probably probable situation is some kind of capture scenario. And the most favored capture scenario comes from Brad Hansen. And he suggested the capture needs to happen very early on when the solar system is still forming. And it can be this kind of direct capture that happens within the disk itself. So it's just using the drag of the disk to facilitate capture into the planet. So yeah, Brad Hansen has a great paper I'd recommend pointing out about that. So short answer is, yeah, theorists can explain it, but they can always explain it. Yeah.
Thanks for your talk. I mean, yeah. I'm also not at all in the field.
Yeah. Yeah, great question. I mean, especially for this planet, it's obvious to imagine that it would have a Galilean-like moon system, which would be multiple moons. When we made our proposal, we were very concerned about this point, and we injected the whole Galilean moon system into the transit and recovered it. And what typically happens, the algorithm we use is called a multimodal algorithm. So it finds multiple solutions, and some of those solutions correspond to real moons, and some of them correspond to like combinations of the moons in kind of strange ways. So if there was a system of moons, we still believe we would definitely detect something, and we would have good confidence there was a moon there. In terms of figuring out which moons are the same moon and combined and how many moons there really are, that would probably require an extensive follow-up program to break all of those degeneracies. Yeah.
Let's thanks again, David. And thank you so much.
Thank you.
Today, we will have a launch for our laboratory here, and it's for a Noel, some kind of the celebration for a Noel.
Oh,
so everyone bring his food, and we will share all our food there.
Oh, nice. Okay. So I can get food there, or do I need to buy food somewhere else? No. Okay. Okay. Hi. Long journey.
Yes. Easier to get the first one. But anyway, you have
Well, we have things that could be the first ones. We're just not sure yet. It's been mostly political. It's been the challenge. Just getting.
I think the time is coming.
Yeah. If we'd have, I was really hoping that once James had launched, it'd be much easier to get Hubble time because it would take pressure off. It's still been very competitive.
For the Kelps time?
Kipping can't observe the Kepler field.
Yeah, it's not Kepler field. That's true.
So
That's true.
a lot of our favorite non-period planets tend to be Kepler planets.
I think for Plato, they're going to observe a bit of the Kepler or not?
No, it's for now, no, in the south, it is not the same field of the Kepler, but apparently there will be one Chinese mission that will observe the Kepler field exactly.
Yeah.
So I think for that, we might have a lot of things.
We did try Cheops for Corot 9. Remember Corot 9?
You tried?
Yeah, we got time, and the observations failed for some reason. Something went wrong. Yeah. So that was frustrating. Yeah, we had the same thing, I think, with Spitzer at one point. I remember we had a Spitzer program with HG to 606, I think, like a second transit. I think we got one previously taken, and we tried for a second, and the observations failed.
No, it ran out of fuel 1 week before.
Oh yeah, that was that. Yeah.
I remember because I remember when we wrote the proposal together.
Yeah.
And then you see, well, 1 week they ran out of fuel.
That was really. It was a true.
Oh my God, that's really bad luck.
Yeah. But yeah, I mean, I'm hoping, obviously with Ariel and Cheops and things, it might be, and Tesla's giving us more targets now. So
Yeah.
That's.
Yeah. But still, the long period planet is very late, especially the one like a Kepler 167, 67.
Yeah,
It's
I really
very long.
I was convinced before this was going to be a walk in the park, and we were going to see like little moons all over the place, and
everything is ideal.
Yeah,
for that one.
Yeah. But yeah, I think we could. I think having a second transit, if we fix, especially some of those exposure things, would help massively. So, but it's going to be a hard sell. But we'll see. There was 4 teams that had the same proposal as us, though. So, Quentin, you probably know Quentin Changeout.
He tried himself.
He was part of our team because he had a competing proposal, and they were both accepted, which doesn't make any sense. His was atmospheres, with a little bit of moons, and ours was moons with a bit of atmospheres. They were both accepted and approved, and so we emailed each other like, "How's this possible?" Because there's only transits every 3 years, so and we had different instrument settings. I wanted near spec, he wanted nearest, so I was like, "There's no way this is possible." And then the panel, the whoever it was, James Webb wrote to us and said, "Oh yeah, sorry, we messed up. Not possible. Yours was ranked higher, so you get the time." And Quentin got shot down. But then we said to Quentin, "Just join us." Yeah. So.
Actually, for us, that we had this exomoon candidate in the past with the 2 models, one which was Jupiter with Earthman as candidates, and then the other option was a Neptune mass planet in orbit of a star that was at high velocity.
Yeah.
because nearly 600 kilometers per second.
Ah.
And then the two were unlikely scenario. But you know, I'm a bit stubborn.
Is this Benedict's paper?
So it was and then the first one was a Bennett paper.
Yeah, Bennett.
And but you know, since I'm a bit stubborn, so I went after it with a cake.
Yeah.
I got the star at magnitude 22.4 in K.
Okay.
So which is basically the limit together with K.
Yeah.
So it means it is a
star system.
It is a star system,
Yeah.
but at nearly 600 kilometers per second. So it's
so it's like a binary star type situation.
No. It's a star that is basically close to the center, close to the bulge, but is being ejected.
Oh wow!
So it's a planetary system that is basically.
Is it on escape velocity?
It's close to the escape velocity.
Wow!
So the two scenarios were bizarre.
Yeah.
But at least we've been able to kill the exomoon scenario. But